students, let us begin with the next content of our derivation. We were dealing with the chapter gravitation, in which we have learnt about acceleration due to gravity. What is meant by acceleration due to gravity? It is nothing but the velocity increase in the given object per second when it is falling under the effect of what? Earth's gravitational pull. And we know that its value on the surface it is 9.8. We have seen the equation for acceleration due to gravity when the object is above the earth's surface. Now let us take the third term, that is acceleration due to gravity when I go below the earth's surface, whether the value for 9.8 remains same or will it change. If it changes, then what is the formula? Let us see that. So we know that our earth, it is basically spherical in nature. So when an object is kept on the surface of the earth, the equation for acceleration due to gravity, we know that it is equal to what? Gm upon r square. So let us denote this equation be equation number 1. Now further we will go with the content that if your earth is a homogeneous medium. What is meant by homogeneous? Homogeneous means it is made up of one or the other type of material, but the composition is the same for all the materials. Even if it is a sand, even if it is other type of soil, the consideration made here when I derive the equation is a bit different. It is said that the earth is homogeneous in nature. Means that even the composition of the object is different. It is made up of different type of materials. It has uniform density value. That is the consideration we are making here. So if your earth is spherical in nature, it has its mass, it has its density, then what is the formula for volume? Volume is equal to 4 upon 3 pi r cube, since it is a sphere. And what we will do here, now we will relate mass with density and volume. And we know the formula for density. Density is nothing but mass occupied per unit volume. So from that I will get the mass formula. Mass will be equivalent to volume into density. So if the consideration made is your earth is a homogeneous sphere having uniform density, then the mass will be equivalent to volume into density. Volume, since it is a sphere, formula for volume of a sphere, it is 4 upon 3 pi r cube. Now here r is nothing but radius of that sphere. So if your earth is considered to be spherical, r, capital R will give you radius of that sphere. Therefore what we have to do, we have to substitute radius as radius of the earth itself. Therefore the formula for volume is 4 upon 3 pi r cube into density is rho. It is the symbol for representation for what? Density. It is pronounced as a rho. Spelling is R-H-O, rho. Okay. So when I substitute, I am getting the formula for mass. So what I will do now, I will substitute this value for mass in our equation number 1. So from equation 1, when I substitute, I am getting acceleration due to gravity small g as capital G as it is, this r square divided by as it is into now the factor mass. So mass is 4 upon 3 pi r cube into rho. So here r square and here r square terms will get cancelled out. The terms which are remaining in the equation are 4 by 3, which is the number you have to take it at the beginning. So therefore 4 by 3, after that you have to write the constants. So constants here are g, pi is a number constant. So pi into rho, the density, and the variable factor means a factor which is changing is your r. So r I will write at the end. So therefore your acceleration due to gravity g will be equal to 4 by 3 g into pi rho r. Okay, let us consider this to be equation number 2. Now we will move on to our basic content that I want to find out the value for acceleration due to gravity at certain depth below the earth's surface. So when I do it, this is the earth. Let us go down below the earth's surface at some depth d. M being mass of the particle which is lying there. Now I want to find out what is the value for acceleration due to gravity here. So for that what we will do, we will imagine a spherical boundary like this which is at depth d. Therefore this distance, that is distance of that point from the center of the earth will be equivalent to radius of the earth minus this distance d. Therefore I am getting what? R minus the distance of that point mass from the center of the earth. Is that clear? So the distance we need to find out, that is small d. So here the object has lied down at some depth d. The distance is r minus d. So if you want to find out the formula for acceleration due to gravity, it is given by the similar as to the only factor here changes is the distance. So the object is lying at a distance of r minus d. Therefore the equation will become 4 by 3 g pi rho as it is into r minus d. Now what we will do, we will divide equation number 3 by equation number 2. We will get gd divided by g. It is equivalent to 4 by 3 g pi rho. It is similar as your equation number 2. So those terms will get cancelled out. The term which won't cancel is r minus d. So r minus d divided by r on the other side. So these terms, that is 4 by 3 g pi rho, will get cancelled out. You are getting what? R minus d divided by r. So further what I will do, I will write the equation in terms of gd. So gd is equal to, I will shift this g over this side, that is over the numerator. We are getting gd is equal to g into 1 minus, how this 1 minus r divided by r, it is nothing but 1 minus d divided by r. I have kept it as it is. So the equation for acceleration due to gravity at certain depth will become g of d is equal to g into 1 minus d divided by r. Let this be number 4 equation. So here we have seen that the acceleration due to gravity, it decreases by a factor of what? D by r as I go below the earth's surface. In the previous equation we have seen that the acceleration due to gravity above the earth's surface was equivalent to g into 1 minus 2h divided by r. So the value for acceleration due to gravity, it decreased by a factor 2 times h by r, whereas here it is 1 times d by r. So as I go above the surface, the rate of decrease is bit higher compared with when I go below the earth's surface. So in both the cases we have seen that the acceleration due to gravity is less than 9.8 as I go above and below the earth's surface. Now in MCQs they will ask you one question, that is, if I go at the center of the earth, what is the value for acceleration due to gravity? So I will use this equation. When I go at the center of the earth, this distance depth d will be equivalent to r. So substitute r here, r by r will become 1, 1 minus 1 0. So this factor will become 0, 0 into g 0. Thus the acceleration due to gravity at the center will be equivalent to how much? It is equal to 0. So when I go above the surface, below the surface, the value for acceleration due to gravity decreases. But as I go at the center of the earth, it is almost equal to how much? 0. Now in this equation we have made a consideration that your earth is sphere, but remember that it is not a uniform sphere. So it is found that the equator is almost some kilometer greater compared with the polar distance. So therefore the value for acceleration due to gravity is not same at the equator and the poles. So at the pole the value is equivalent to 9.83 meter per second square, whereas at the equator the value for acceleration due to gravity is found to be equivalent to 9.78 meter per second square. So it is basically due to the difference in the distances between poles and equators. Okay, so we'll move on to the next content, that is gravitational potential energy. So what is meant by gravitational potential energy? It is nothing but the energy possessed by the object when it is under the effect of Earth's pull and it is at rest. So we know that the total energy is being convertible into two forms. One is potential energy, another is kinetic energy. So when the object is at rest, the energy possessed is nothing but potential energy. When the object is under motion, the energy possessed is nothing but kinetic energy. So when the object is at rest, being kept under the effect of Earth's gravitational pull, the energy stored in it is called as gravitational potential energy. So when the object is left, it will move down and this potential energy will slowly get converted into kinetic energy, and due to that the object will get displaced by certain. Okay, so if you want to find out how much is the change in the potential energy, that can be calculated by seeing or finding out the value for work done. Work done is nothing but force into displacement. So when I apply any force on a given object and the object will get displaced by certain distance, then work done on the given object will be equal to force into that distance, or it is nothing but displacement, which is a vector quantity. Thus, work is nothing but force into displacement, or it is nothing but change in the potential energy, means how much change in the potential energy has been occurred. So when the object is flowing under the effect of Earth's gravitational work, energy, this potential energy will be used to do some work on it, and we will see the equation for that potential energy. So let us consider Earth to be spherical in nature. R is the radius of the Earth. I want to find out the potential energy at certain distance r from the center of the Earth. So before that, I will choose one point A, which is lying at a distance x from the center of the Earth. So if the mass lies here at point A, what is the force of gravity acts on it? F is equal to gmm upon x square. M is mass of the Earth and x is the distance of the point from the center of the Earth. That is, therefore it is divided by x square. That is the equation number 1. Now let us shift this object from A to B due to the gravitational pull. The object will get displaced. Let the distance which is covered is very small, and let that be equal to d of x. So to do this displacement, how much amount of work is been done? So therefore work done, which is very small, is equivalent to F into dx, force into displacement. So this is the amount of work done, which is very small. Therefore I have denoted by d of w. Very small displacement, therefore d of x. Thus a small amount of work done is equal to F into dx. Now the object, the equation will become gmm upon x square when I substitute the value for F into dx square. Now here I want to find out the total work done on the given object when it is moved from infinity, very larger distance at certain point P. Now to do that, what we will do, we will find out the work done from P to B, from B to A, from A to something, and so on up till infinity. And we will add those work, W1, W3 and so on up till Wn. But that process is very lengthier. So for that we will just apply one more component, that is known as integration. So for that you need to know initial value and final value, apply the formula, then you will find the value. Integration you will study in detail in your next year maths. Just we will take certain formulas to solve the equations here. Okay, so when I apply integration, you need to concentrate here, that is integration from what point to what you are doing. So integration to some distance x is equal to r from x is equal to infinity. So when I apply integration, this is the representation for integration. X is equal to infinity to x is equal to r. Which factor we are integrating? dw, that is equation number 2. So when I integrate this equation 2, what I am getting? I am getting integration of this factor, it is 1 into dw. So 1 is nothing but w raised to 0, let us assume. So when w raised to 0 is there, when I apply the formula here, w raised to 0 into dw. This is the formula for integration. Integration of x to the power n into dx with respect to what? Which is the variable. Okay. So here w raised to 0 equation will become, which is equal to w raised to 0 plus 1, n plus 1 divided by 0 plus 1, n plus 1. Therefore it is becoming w. So integration over this side is w, and from this side gmm upon gmm is a constant taken outside the integration. So integration of again x is equal to infinity to x is equal to r. So this is known as lower limit, that is initial value. This is known as upper limit, the final value. When I apply integration to this factor, x is a variable, so I have kept it inside the integration. When I apply the formula here, the term will become x to the power n is 2, 2 plus 1. Okay, x is at the denominator. When it is brought here above, it will become minus 2. Therefore, it is minus 2 plus 1 divided by minus 2 plus 1 will become how much? X to the power minus 2 plus 1 divided by minus 2 plus 1. Therefore, it is equivalent to x to the power minus 1. Therefore, I have kept it denominator, and minus 2 plus 1, it is nothing but minus 1. Therefore, the terms will be minus 1 divided by x when I integrate 1 upon x square. So, further you need to apply the upper and lower limit. So, the formula is, in place of x, you have to substitute first this upper limit minus, in place of x again you have to substitute the lower limit. So, when I do that, I am getting minus gmm as it is. So, minus I have taken here. So, minus gmm 1 upon r minus 1 upon infinity. That is, first upper limit minus lower limit substitution you have to do. 1 upon r as it is, and 1 upon infinity is nothing but 0. So inside the bracket you are getting 1 upon r minus 0, or when I simplify I am getting w is equal to minus g and m upon r. And this is giving you the amount of work done when I shift the object from infinity to point P at a distance of small r from the center. Okay, and this work done is nothing but how much change in the potential energy, or how much is the potential energy at point P. So therefore work done will be stored in the form of potential energy, and that potential energy is nothing but W, or potential energy is nothing but from this equation number. Let us rename this as equation number 3. So from 3 you are getting minus Gm upon R. Let this be equation number 4. And this equation is giving you the value for potential energy of the object at certain point R. See that we have a negative factor, indicates that the value is decreasing into Gm upon R. R is the distance. See that it is to the power 1. R is to 1. So potential energy is found to be inversely proportional to R. So sometimes CET will ask this type of question. It is inversely proportional, directly proportional. How? What power? In that case you can see these or concentrate on these formulas. So now we have completed the formula for gravitational potential energy at certain distance r from the center of the earth. Thank you.